Okay, this is video 10 and it's on Newton's law of universal gravitation. So what is that all about? If we're talking about gravitational forces, we're talking about forces of attraction between two masses. So any two masses in the universe, mass 1 and mass 2, would be attracted towards each other, according to his law. These are gravitational forces of attraction, and although these two masses have different masses, the forces of attraction are identical. That comes from Newton's third law. So mass 1 exerts a gravitational force on mass 2. At the same time, mass 2 exerts a gravitational force of attraction on mass 1. So what does this gravitational force depend on? Well, in his statement of his law, he says that this gravitational force is directly proportional to the product of the two masses. So we need to multiply those two masses together to find the gravitational force between two masses. He also goes on to say that this gravitational force between the two masses is inversely proportional to the distance between their centers squared. So we call this an inverse square law, where the larger the distance between the two masses, the smaller the gravitational force becomes. So if we put these two relationships that are in his law together and we introduce a proportionality constant, we'll get that the gravitational force is equal to this proportionality constant, which happens to be the universal gravitational constant, multiplied by the two masses that are attracting each other, and divide that by the distance between their centers squared. So this formula you'll find on your data sheet, and it's used to calculate a gravitational force acting on both masses. Let's just talk about this universal gravitational constant. It's a constant you'll find on your data sheet. It has a value of 6.7 times 10 to the minus 11, and its units are newtons meters squared per kilogram squared. That gravitational constant is constant throughout the universe, so we can use it for any planet or any part of the universe. R was the distance between the centers of the two planets, for example. So be careful not to take the distance on the surface of planets, but rather the distance from the center of each planet must be used. And another important point here is that R must be in meters, not kilometers. So don't substitute kilometers into this equation. You need to first convert to meters, and then don't forget to square that distance. And obviously our two masses in question, mass 1 and mass 2, though the unit of that should be the kilogram. So let's go and have a look at the statement of Newton's law of universal gravitation. And let's go and find it. Here it is here. So all those relationships are in here. So it talks about every particle with a mass in the universe. Every single particle that has mass in the universe is attracted. So it's always going to be a force of attraction to every other particle in the universe with a force that is directly proportional to the product of the two masses. So that's m1 times m2, and inversely proportional to the square of the distance between their centers. So there's the distance between their centers don't forget to square that distance and make sure that it's in meters. The other important thing I'll say again is that each mass experiences the same gravitational force. So if this was the Earth and that was the Moon, the force that the Earth exerts on the Moon is exactly equal to the force that the Moon exerts on the Earth. And that's according to Newton's third law. So let's go back to a couple of examples of applying this law. So the first example is a man standing on the surface of the Earth. So this is the Earth. And there's a man on the surface, and his mass is 70 kgs. The mass of the Earth is given to you to be 6 times 10 to the 24 kilograms. And what we need to find is the gravitational force acting on that mass, that man. What gravitational force is he experiencing standing on the surface of the Earth? So I want you to pause the video, apply Newton's law of universal gravitation to the problem, and try and find that gravitational force. Okay, since you've tried the problem, we're going to apply Newton's law of universal gravitation to the problem. Right, so we take the equation from the data sheet. G is our constant, that's the mass of the man, that's the mass of the Earth, and that's the distance between their centers. Here's the constant straight off the data sheet, 6.7 times 10 to the minus 11. There's the mass of the man, and there's the other mass, the mass of the Earth. We've got to be careful here because the radius of the Earth was given in kilometers, so we need to convert that. We know that the distance between the two masses is just the radius of the Earth, because that's the center of the Earth and that's the center of the man on top of the Earth. So the distance between their centers is the radius of the Earth. But we're given the radius of the Earth in kilometers, so we need to multiply that by 1,000 to get that into meters. So that's now in meters. There are 1,000 meters in a kilometer, and then we substitute it into our equation. 6,400 times 10 to the 3, and then don't forget to square the entire distance. Well, if you put that correctly into your calculator, and you get 687.01 newtons, that's a force. It's a force of attraction. And that's then the direction of your force, because force is a vector, it needs direction. And the direction of this force here on the man is towards the Earth, towards the center of the Earth. And we also know that at the same time, the man exerts the same force on the Earth upwards towards him. We could calculate the gravitational force in another way, by knowing the mass of the man and the acceleration due to gravity of 9.8, and that gives us a very similar answer. The reason why these two would differ is because that is not as accurate as we would want. The radius of the Earth is more accurate than that, and certainly the mass of the Earth, the value of that is more accurate than the one we're using. But more about acceleration due to gravity later in this topic. So at the moment, that's the way we wanted to solve this problem. So please don't forget to give a direction, attraction, or towards the Earth in your final answer. The next question is about a satellite. This satellite has a mass of 200 kilograms and it's orbiting the planet Mars. It follows a circular orbit around Mars, and it's a certain distance from the center of Mars. We've got the mass of the satellite. Here is the mass given to you of Mars, 6.39 times 10 to the 23 kilograms, and we're given the radius of Mars at 3,400 kilometers. So we've got the radius of Mars, and we want to, well, we know that the satellite is orbiting at a height of 2,000 meters above the surface of Mars. And you need to find the gravitational force acting on that satellite. So pause the video, find the gravitational force acting on the satellite, and then come back to check your answer. Okay, so here's a view of the planet Mars, and we've got the circular orbit of the satellite, and we're trying to find the distance between their centers. And we know the radius of the planet to be 3,400 kilometers, but we also know the distance above the surface. So we need to put these two distances together. These two distances together need to be added together to get the distance between the centers of the two masses. So we've got to add 3,400 kilometers to 2,000 kilometers, because that's the height above the surface, and that's going to give us 5,400 kilometers, which we need to convert to meters. So 5,400 times 10 to the 3 meters. That's the distance between the centers of these two masses. And then it's a case of going to the equation for finding the gravitational force and substituting everything in. The gravitational constant, the mass of the satellite, the mass of Mars, and then the distance between their centers. Don't forget to square it. That gives you 293.64 newtons, and again it's an attractive force. So the satellite is experiencing a force of attraction of 293.64 newtons, and at the same time Mars itself is attracted towards the satellite with that same force. That force is so small it's not going to influence the path of a much larger mass. Mars has a much greater inertia than the satellite because it has a larger mass, and therefore it's not going to be influenced. It has a greater resistance to any change in its motion. So there we go, we've found the attractive force, gravitational force on that satellite. Let's look at a third example. And this example, we are looking at planet X. There's a mass sitting on the surface of planet X. Planet X has a radius r. It has a mass capital M. We then take that same mass and we take it to another planet, planet Y, and it's resting on the surface of planet Y. Planet Y has different dimensions. It's got a radius of twice that of X, double the radius. It's got a mass 3 times larger than the mass of planet X. And here's the first question. By what factor would the gravitational force change when that mass is now on planet Y? So we're taking the mass from planet X to planet Y, and we're saying by what factor would that gravitational force that it's experiencing here change when it gets onto planet Y? Does it get larger? Does it get smaller? Well, that's up to you to find out. So pause the video and attempt to find this factor that we're talking about that relates the one force F. That's the force on planet X. What's the new force on planet Y? So pause the video and try that one. Okay, so we need to write down an expression for the force acting on this mass on planet X. And according to Newton's law of universal gravitation, it's G multiplied by the mass of the objects on the surface multiplied by the mass of the planet X divided by the distance between their centers. And the distance between the centers of these two masses would just be the radius of that planet. They're 1 radii apart. So we'd pop r in there, we wouldn't forget to square it, and that would be an expression for this gravitational force on that mass on planet X. Well, then we move our attention to y and we say, well, what is the new force acting on that mass? Well, the universal gravitational constant doesn't change throughout the universe. Mass m hasn't changed. We're still at the same mass on a different planet. And the mass of the planet has changed. So now the new mass is 3 times the mass of planet X. So we put 3m in there. And then we divide it by the new distance between the two masses. Well, again, this mass m is the radius of planet y away from the center, and the radius of planet y in terms of the radius of planet X is 2r. So we're going to have to put the new distance between the two masses in and not forget to square the entire thing. It's not correct to write 2r squared, because the new distance is 2r, and that new distance has to be squared. Okay, so let's work with this expression. In the numerator, we've got a 3 that we could bring to the front, and we've got G, M, capital M. So the order in which we write that doesn't matter, but we want to bring that factor to the front. And here at the bottom, when we square 2r, we get 4r squared, and then we'll recognize this expression as the original force. So this expression in brackets here was the force on planet X. So let's replace that with F, and the new force on planet Y is 3/4 of the old force. So it turns out that the force on planet Y is smaller than the force on planet X. The second question is the following. Also need to find another factor. By what factor would the gravitational force change if you were 2 radii above the surface of planet X? So let's go to that picture of planet X. Well, I'll just draw it over here. We've got planet X, and we had that mass on the surface, so it was 1 radius away, and now we're taking that mass to a further 2 radii away from the surface of the planet. So pause the video and find that new gravitational force acting on that mass. Okay, so you've tried that. And let's write an expression. Well, we've got the expression for when the mass was on the surface. We've already got that expression for the gravitational force on that mass. That's on the surface. But now we get a new force when we move it away. Gravitational constant hasn't changed. The mass hasn't changed. The two masses haven't changed. It's still the same planet and the same mass, but the only thing that's changed here is the distance between their centers. And you'll notice here that the distance between their centers is not 2r, but rather 2r plus another r. That gives you 3r. So if we put that new distance in there between their centers, new distance is 3r, and we have to square all of that. And that's going to give us a factor in the denominator of 9. Well, this expression over here is the old force. So the new force is 1/9 of the old force. So this is an example of an inverse square law, where if we triple the distance between their centers, then the force is 1/9 of its original value. So increasing the distance decreases